Hello, welcome back to the probability class. Today we will talk about Bayes theorem and multiplication rule. Let me first bring out the PPT. Here it is. Conditional probability, a quick recap. It means probability of A given B where A and B are two events. What does it mean? It's given that the event B has occurred and we are trying to compute what's the probability that event A has also occurred. It's defined by the formula probability of A given B as this expression. Probability of A intersection B divided by probability of B. And we use this shorthand AB for A intersection B. In the last session, we talked in details what's conditional probability, saw different examples. Then we talked about pairwise independence, mutual independence, etc. Let's go to the next slide. Let's consider a collection of events. We are heading towards Bayes theorem. Consider a collection of events B1, B2 up to Bn. Then that is called mutually exclusive. I repeat, mutually exclusive. If any two events from this collection are disjoint. In other words, Bi intersection Bj is equal to null set whenever I is not equal to j. So the diagram is like this. Here is B1, here is B2, here is B3. They do not intersect with each other. So this is a correct example for mutually exclusive collection. However, if you have B4 intersecting with B1, if this is B4, then this is not mutually exclusive. Clear this? The collection will be called exhaustive provided they cover the whole sample space. In other words, B1 union B2 up to Bn, that is whole of the sample space. The diagram is like this. Say, here is B1, here is, this one is B2, and suppose this part is B3. This part is B3. And the whole thing is sigma. You see, union of B1, B2, and B3 gives the whole sample space. So this is exhaustive. However, if you have like this, say, so this is exhaustive. However, if you have B1, this is your omega, B1 and B2, and suppose B3 is this, then they do not cover the whole sample space. So this is not an example. Let me give you some examples of both. Consider coin toss twice. So what's the sample space here? Sample space here is equal to HH, HT, TH, and TT. And what are we doing here about the experiment? Toss a fair coin twice. Now consider your B1 as B2. Suppose B2 equal to if you now take B1 and B2, this is a collection, B1 and B2. This collection is mutually exclusive. So B1 and B2, this is mutually exclusive because B1 intersection B2 is null set. However, the same collection B1 and B2, is it exhaustive? Is their union the whole of the sample space? The answer is no, because their union gives only HH, their union gives only HH, HT, and TH, but it doesn't give you TT. That's why B1 and B2, this collection is not exhaustive. Not exhaustive. For the same example, our omega is HH, HT, TH, and TT. We are considering the same random experiment. Now consider this. Say B1 equal to HH, HT, B2 is equal to HT, TH, and B3 equal to B3 equal to TH and TT. In that case, union of B1, B2, and B3 gives the whole of sample space. It covers HH, HT, TH, and TT. All the four outcomes are covered by this B1 union B2 union B3. So here, this collection B1, B2, B3 is exhaustive. Now the question is the collection mutually exclusive? The answer is no, because you see B1 and B2, they intersect. B1 intersection B2 is what? B1 intersection B2, this with this, you get the common element HT. Same omega, HH, HT, TH, and TT. Take now B1 equal to HH, HT, B2 equal to TH, and B3 equal to TT. What happens to this collection? If you take B1, B2, B3, these three sets or these three events together, then they are mutually exclusive because none of the three sets intersect with each other, and also exhaustive because their union of B1, B2, and B3 gives you the whole sample space, namely this one. Excuse me. Let's go to the next slide. We are heading towards Bayes' theorem, and here is one step. Law of total probability. Suppose B1, B2, Bn is a collection of mutually exclusive as well as exhaustive events. That means the diagram is like this. Say here is B1, here is B2, here is B3, here is B4, and so on, and here is Bn. So they do not intersect with each other. At the same time, their union covers the whole sample space. In that case, probability of A nicely decomposes into n terms. It is the summation of n probabilities, namely probability of A intersection B1 plus probability of A intersection B2 plus ... probability of A intersection Bn. So it decomposes into n probabilities, and those are the n terms. Say here is A. Suppose this is A, then it decomposes this way. Alternatively, the same formula can be written as this thing. In place of AB1, you can write this thing. And AB2 can be replaced by this. Let's see why. In other words, we are replacing probability of ABI by this thing. And that should be easy to see. Once we know this thing, for the time being, assume that we have already got this thing, then getting this thing is easy because probability of A given BI, is nothing but P of ABI divided by P of ABI, P of ABI divided by P of BI. Now, if you bring P of BI on this side, on the left-hand side, then you get P of ABI is equal to this multiplication. And that's why this formula follows from this formula. Okay, we will see why it's true. Why it is true? Let's see why this statement holds. Let me take the pen. B1 to Bn, they are exhaustive. It's given. That means B1 union B2 union Bn is equal to omega because of exhaustive. if you intersect by A, by the way, what's A? A is any other event. I should have mentioned that thing earlier, but it's written over here. A is any other event. B1 to Bn is a collection of mutually exclusive and exhaustive events, and A is any other event. Because they are exhaustive, we are getting this thing. Now let's intersect by A on both sides. So the left-hand side becomes and right-hand side becomes. Now, after this, actually, had I got a whiteboard there in the next slide, it would have been easier, but I forgot to keep a white space there. Anyway, left-hand side, by distributive law of intersection over union, I can write it as A B1 means A intersection B1, union A intersection B2, union A intersection Bn, and the right hand side is equal to A because A is a subset of omega. In fact, all these events B1 to Bn and A, they are all subsets of omega. That's why A intersection omega is equal to A. Now let's observe something here. B1 or B1 and B2, they don't intersect, right? So this is null set. The diagram is like this. Here is B1, here is B2. So what should happen about AB1 and AB2? Should they intersect? No, because AB1 is somewhere within B1, right? It's a smaller part than B1, and so is AB2. Because AB1 is part of B1 and AB2 lies here, they also do not intersect. Similarly, AB2 and AB4, they also do not intersect. In other words, ABI intersection ABJ is null set for I not equal to J. In other words, the collection of events AB1, AB2 up to ABN, this collection is mutually exclusive because of this one. So this is a mutually exclusive collection. And what happens for mutually exclusive collection? Because they are all disjoint, by the inclusion-exclusion principle, the probability of the union should be summation of the individual probabilities. So probability of union, probability of AB1 union AB2, we are applying inclusion exclusion principle. You remember we had talked about inclusion exclusion principle, and we had given the example of non-overlapping areas. When you try to find out non-overlapping areas, then the areas just add up, and similar things happen when the events are non-overlapping. So here, the probability of this union will be nothing but the summation of the individual probabilities. So probability of AB1 plus probability of AB2 plus probability of ABN. So this one, once we got this, then we take probability on both sides, and while taking probability on the left hand side, that breaks down as this thing. That's why we can write the left hand side probability as P of AB1 plus P of AB2 plus P of ABN, and the right hand side is nothing but a PA. See, to come from here, from this step, we just took probabilities on both sides. That we can do, because if two events are same, their probabilities will also be the same. But remember, not the other way around. The two events may have same probabilities, but the events might be different. So you have got this formula, and that's precisely we had to prove this one. Hence the proof of the law of total probability. Law of total probability. Let's go to the next slide now. Bayes rule. Bayes theorem. Suppose B1 to Bn is a collection of mutually exclusive and exhaustive events, like the law of total probability. There also we had this assumption that B1 to Bn is a collection of mutually exclusive and exhaustive events. So it's here. And let A be some other event. In that case, probability of B1 given A turns out to be given by this formula. This formula looks very long and frightening. Actually, it's very simple. But for the time being, don't bother about the details. Just look at the expression and remember there is something. We'll come to that, what it means. But before we proceed further about Bayes theorem, about proof, or say the mathematical expression, let's see what it is trying to do. Say, here is B1, B2, B3, B4 maybe up to B4 we have. So B1 to B4, suppose, is a collection of mutually exclusive and exhaustive events. A is some other event. You are told that A has occurred. You are told. This is given to you. Under such a incident, you are trying to find out the chance of B1 having occurred, or B2 having occurred, or B3 having occurred, and B4. In other words, it's given that A has occurred. You are doing some kind of back calculation. How much is the probability of B1 given A? How much is probability of B2 given A? You know, one of these four events must have occurred because they are exhaustive. Remember, exhaustive means what? One of them, at least one of them must have occurred. And because they are mutually exclusive, you know, only one happens. Only one occurs. So always B1 to B4, because they are mutually exclusive and exhaustive, exactly one of them must occur always. It's given that A has occurred, and you are trying to compute or you are trying to conclude which one has occurred, whether it is B1 or B2 or B3 or B4. That's why you are trying to compute these probabilities, P of B1 given A, P of B2 given A, P of B3 given A, and P of B4 given A. An interesting analogy with detective story. Detective comes to the murder spot and observes that there are 3 ways to reach the spot by means of 3 doors or whatever. And he believes that to proceed further, it's needed to first come to a logical conclusion which route is followed by the murderer. So he makes observations, interrogates people, and gathers circumstantial evidences to come to the conclusion which route is followed. Here, circumstantial evidences and interrogating people, observations, all these things are what is given to us. The event A has occurred. And we are trying to find out which event has actually occurred. But unlike the detective, here we don't pinpoint that this is the event what has occurred or which has occurred. Instead, we give the probabilities of each having happened under these circumstances. That is, how much is probability of B1 given A, how much is probability of B2 given A, etc. Like giving the probability of 3 different routes for the detective instead of pinpointing which one. Then it's the job of the detective to decide which route is actually followed. So Bayes' theorem gives you probabilities for all these different routes. So in that sense, Bayes' theorem is also some kind of back calculation or trying to conclude something about what must have happened actually. Let's move to this. Here is the proof. We are trying to compute this thing. And by definition, that's nothing but P of B1A by P of A. B1A is same as AB1, so we write this way. And probability of AB1 can be written this way, because if you start from here, you will get here. What's P of AB1? P of AB1 is nothing but, sorry, P of A given B1 is nothing but P of AB1 by P of B1 multiplied by P of B1. That gives you P of AB1. And that's what is this thing, this step, from here to here. Now, P of A by means of total probability, the theorem of total probability we saw, that helps us write probability of A this way, because B1, the collection B1 to Bn of events, that's mutually exclusive as well as exhaustive. So we can write P of A as this. That's why P of B1 given A, that can be written as this big formula. Probability of A given B1 multiplied by probability of B1 divided by you get this. Okay. So here, look at this formula. In order to understand this thing, you are trying to do back calculation, right? How much is the probability of A given B1? Often what happens, the forward probability calculations are a lot easier, or the way the structure is built, often the forward direction probabilities, forward direction conditional probabilities like P of A given B1, that's what I'm calling forward moving conditional probabilities, P of A given B2, often the way our real life scenario is structured, often these things are a lot easier to know or compute. However, the other way around is not so easy. Often that's the scenario. And if that is the scenario, then how do you compute this thing? You reverse the conditioning by this formula. See, that's what we are doing. Here it's backward conditional probability, if I may use the terminology. That's not a standard terminology, but I'm just using for your for the sake of your understanding. So backward conditional probability can be broken down into forward conditional probabilities like this, everything given in terms of conditioning with respect to BIs by this formula. First, it's a ratio of two things. The numerator is just the order is flipped. Probability of A, you are trying to compute P of B1 given A. And in the numerator, what you get is P of A given B1 multiplied by P of B1. And once you get this expression, the denominator is a repetition of those things with all other i's, not only one B1, but with B2, B3 up to Bn. See, that's what it is. P of, first we repeat this, whatever is written here in the numerator as the first term of the denominator, this one. Then the second term is nothing but the same as the first with only B2 replacing B1 and so on. And the last term is nothing but Bn replacing B1. Let me go to the previous one. Okay. Previous one. Yeah. See the expression here? P of B1 given A is equal to, the numerator is, we are just flipping the order. Instead of B1 given A, here we have got P of A given B1 multiplied by P of B1. And in the denominator, we have got all n terms. First term is same as the numerator, plus whatever the first term, replace B1 with B2 and so on. And that way you get n many terms. That's what gives you the denominator. And the denominator comes from the law of total probability. Once you understand the way it's written, it's actually very easy. The expression as such looks frightening, but actually it's not. Let's illustrate this formula with the help of this example. There are three machines, X, Y, and Z. that produce 60%, 30%, and 10% respectively of the total number of items of a factory. The item may be anything, pen or mobile, anything. In a factory, there are 3 machines producing same kind of outcomes. Machine X, Y, and Z. So this one is producing 60%, 30%, and 10%. Now, no machine can produce all the items in good condition, I mean properly. There will be some mistake or some bad elements or some bad items will be also produced inadvertently, but there will be some mistakes. So that data is given. Among the outputs of the machine X, only 2% are defective. 2% are defective. And the production of machine Y has got 3% defective items, and the items produced by machine Z has got 4% defective items. That's given. Now imagine that all these products or items produced by X, Y, and Z come to a common place, the storehouse. And once it arrives at the storehouse, there is no separate segregation of the items. They're all mixed up. And what happens? A few randomly selected items from there go for quality check, and it's determined whether it's in good condition or it's defective. In other words, you can visualize that the quality inspector randomly picks up an item and determines whether it is okay or defective. Now, read the next part of the question. An item is selected at random. An item is selected at random. That means the person is picking up one item randomly and found to be defective. The quality inspector finds the item to be defective. Now, the question is, what's the probability that it was produced by machine Z? And maybe if it is produced by machine Z, they will inspect machine Z more closely and find out if they can rectify it somehow. Probably that's why they are asking the question, how much is the probability that it is produced by machine Z? That's the question. Now, for this, we will first identify some events. By the way, what's the random experiment here? The experiment is random selection of an item. That's the random experiment. And let's talk about these events. Say event A. Let me go to the next board. Or next slide. I think it's written over there. Yeah, here it is. Let us consider the following events. Event A means the selected item. One item is selected by the quality inspector. The selected item is produced by machine X. It may happen or may not happen. We are just talking about the event here, or we are identifying the event as a that the event is what's the event A? The selected item is produced by machine X. Similarly, event B is the selected item is produced by machine Y, and here is C. similarly produced by machine Z. And there is also an event D, namely the selected item is found to be defective. Okay. Now, when the inspector picks up an item, the event D might occur or may not occur. The item may be defective or may not defective. And that's true for all these events. The picked up item might have been produced by machine X or machine Y or machine Z, or it may be defective. So any of these four events might have occurred or might not. Right? Now, what's given in the question, or what we are given, is that event D has occurred because we are told that the quality inspector, whichever item he or she picks up, that item is defective. The item is found to be defective. So it's a conditional probability question. We are trying to compute under such a scenario, what's the probability that the item is produced by machine Z? In other words, we are trying to compute this conditional probability of C given D, and given D because the selected item is given to be defective. So we are trying to compute this probability. Now let's look at the collection A, B, and C. Are they mutually exclusive? Can A and B happen simultaneously? Suppose they can. Suppose it's possible that both of them happen simultaneously. What does it mean? That means there is an item which is produced by machine X as well as machine Y, because the event A means the item is produced by machine X, and event B means the item is produced by machine Y. So the same item in that case is produced by machine X as well as machine Y, and that is not possible because one item is produced by one machine only. So they, A and B, cannot intersect. In other words, A intersection B is null set, so is BC, and so is CA. That's why this collection is mutually exclusive. Are they also exhaustive? The answer is yes, because any selected item must have been produced by either machine X or machine Y or machine Z. So one of the three events, A, B, or C, must hold good or must have occurred. That's why this is exhaustive. So this collection ABC is a collection of mutually exclusive events which are also exhaustive. So the precondition of Bayes formula is true here. Bayes condition Bayes theorem we can only apply when certain precondition holds, namely B1 to Bn is a collection of mutually exclusive events and exhaustive events. So that precondition is holding here. Let's clear this. Go to the next slide, the calculation part. Okay, we are supposed to compute this. Now, writing this way, just try to write it yourself. The numerator is nothing but conditioning is flipped. Instead of probability of C given D, it becomes probability of D given C, and you multiply by the probability of C, and the denominator becomes all these things summed together. Now let's see what are all these terms. numerically. What is probability of A? We are given that machine X produces 60% of the products. That means probability of A is equal to 60 by 100, that is equal to 0.6. Similarly, probability of B is equal to 0.3, and probability of C is equal to 0.1 because machine Z produces 10% of the items. How much is probability of D given A? That is the percentage of defective items produced by machine X. And we are given that 2% of items produced by machine X are defective. And that percentage in terms of probability is nothing but percentage divided by 100. That's why it is 0.02. Similarly, probability of D given B is equal to 0.03 and probability of D given C is equal to 0.04. So we have got all the things needed to apply this formula. Let's put all these terms. The numerator turns out to be 0.04 because that's what is probability of D given C, and probability of C is equal to 0.1, and so on. We put all these figures. 0.02 comes from here, and 0.6 because of PA is 0.6. Probability of D given B is 0.03, this one, and probability of B is 0.3, this one. P of D given C is 0.04 and probability of C is 0.1. After evaluation or simplification, you get 4 by 25. All right, multiplication rule. Multiplication rule, again, a long-looking expression, but once you understand the rhythm of the formula, it becomes easy to remember. Unlike Bayes' theorem or the theorem of total probability, B1 to Bn, we had the events B1 to Bn there, and those were mutually exclusive as well as exhaustive. Here, we have got n events A1 to An, but we do not demand any such condition out of this. Those are any n events, are any n events. Then, probability of this intersection can be calculated as this long-looking expression. Let's understand the rhythm of the formula. Probability of A1, that comes first. First observation is it's a multiplication of several terms. You are trying to compute the probability of the intersection, and that is decomposed as product of n terms, probability of A1, probability of A2, etc., etc. First probability of A1, in fact, it's product of n probabilities. First term, probability of A1 is without any condition, unconditional. The second probability of A2, that is based on the information given by A1, probability of A2 given A1. Then probability of A3 given both A1 and A2. And when you try to compute the probability of An, all the earlier events are given. That is probability of An given A1 as well as A2 as well as An minus 1. Once you understand that, writing this formula becomes easy. Why it's true? Come from the right hand side. That becomes easier to do. P of, let's write down the right hand side or expand the right hand side. P of A1 comes as it is. probability of A2 given A1 is nothing but this P of A2 A1 divided by P of A1, just from definition. And again, applying definition, we get this. From here, we get the numerator should be probability of A3, A1 and A2, but that is same as probability of A3, A2, A1, because after all, this is nothing but intersection of three terms, or intersection of all the three events A1, A2 and A3. And from here to here. Now, after having written this way, see, lot of things will cancel out. This will cancel with this, and this with this. Similarly, although not written, this will cancel out, and so will be this one. And the only term left will be this one. That's why we get probability of A1, A2 up to AN. And that's precisely the left-hand side. So that proves multiplication rule. Let's see an application of that thing. It's very useful when the things look complicated, and more information you have, it helps to calculate the probability. Because conditional probability means what? You are given some information, and more the information, often the complicated scenario becomes a lot easier to sort out when you are given some information. That's the real use of this. And in the next example, you will see how that thing helps. Clear the board. Suppose an urn contains Suppose an urn contains 4 red and 3 white balls. Four red balls, and 3 white balls. Other than the color, the balls are identical, and you blindly pick up one randomly. One ball is randomly picked up from the urn. And after picking up the ball, you observe the color, and after observing the color, you replace the ball back in the urn. So first you pick up a ball from the urn. That's the experiment. Observe the color. First you take it out and then put it back. And not only that ball, you replace the ball along with another ball of the same color. That's what this one says. After observing the color of the ball, it's replaced along with another ball of the same color. So if the picked up ball is red, after observing the color, you put the ball back and add another red ball to the same urn. In that case, the urn will have 5 red balls and 3 white balls. However, if the picked up ball turns out to be white, then what you do is you replace the same white ball into the urn, and then you put another white ball in the same urn. In that case, the urn will contain 4 red and 4 white ball after the experiment. Now, what you do is you repeat the process 2 more times. That is, 2 more times you pick up one ball from the urn, observe the color, replace it along with another ball of the same color. So repeat this process 2 more times. So how many times we are repeating the same process? 3 times. 3 times we are doing the same thing. And that's the total experiment. Please understand. That's the total random experiment. And at the end of the random experiment, how many balls we will have in the urn? 3 more balls will be added. To start with, we have got 7. So when the experiment is performed, after the performance of the experiment, to start with, we had 7. After the experiment, we will have 10. Right? So here we have 7. After the first repetition, we have got 8. After the second, we get 9. And after the third, we get all the 10 balls here. So that's the total experiment. Now, look at the question. Find the probability that a red ball is drawn each of the 3 times. This is what we need to address. What's the probability that a red ball is picked up each of the 3 times? Let me go to the next slide. Here are some events. Consider the following events. By the way, on many a slide, you will see these kind of things. Consider THE, and there is a huge space in between. Almost like as much as we can put a word almost. This is beyond my control. Sometimes when I try to write a word in this particular thing, then what happens? It gets split into this kind of things, and I cannot really manage to write it as THE. So please bear with me. And when you see this kind of things like independent, you will sometimes see that's written as independent, and then independent. It's written as independent, and then after a gap, you see T. So please bear with me when you see these kind of things and make the mental correction. Okay, let's get back to the example. Let's consider the following events. R1, that means the first drawn ball is red. That's an event. R2 is the event that the second drawn ball is red, and R3 is this event, the third drawn ball is red. After having written the events like this, what's the event that all the 3 picked up balls are red? That is nothing but R1 intersection R2 intersection R3. So we are trying to compute probability of that. And here, multiplication rule will come handy. Multiplication rule allows me to write this probability of intersection as P of R1 multiplied by probability of R2 given R1. Remember the form. And probability of R3, when we are computing probability of R3, all the previous things are given, that is R1 and R2 are given. Now see the beauty of the multiplication rule. Probability of R1. R1 means what? It is talking about only the first trial. There are 3 trials, right? Here there are 4 red and 3 white. What's the probability that when we are picking up a ball from here, the picked up ball is red? That's what is R1. That probability, you should not have any difficulty in agreeing that that probability should be 4 by 7, right? Because there are 4 red balls out of total 7. So probability of R1 should be 7. Now, if R1 is picked up, because next time we are to calculate what is the probability of R2 given R1. R2 given R1. Now, if R1 occurs, then what will be the configuration of the urn? There will be 5 red and 3 white balls. The configuration changes this way. So given this configuration, how much should be the probability of getting a red ball? That is, how much is the probability of R2 given R1? That should be equal to 5 by 8, because total number of red balls here is 5 and total number of balls is 8. So probability of R2 given R1 is 5 by 8. Now, what should be probability of R3 given R1 R2? Given R1 R2 means in the next round also we got red. So the configuration now is 6 red balls and 3 white balls. So the probability of R3 given R1 R2 should be equal to 6 by 9. Now let's multiply all these things. So probability of R1 probability of R1 R2 R3 must be equal to multiplication of all these things, 4 by 7 multiplied by 5 by 8 and 6 by 9. You simplify this, you get 5 by 21. Because 6 and 4 will cancel out, with 8 and 3 out of this thing, you will get 5 by 21. That's the answer. Understand the moral of this, or the gist of the procedure we followed. Here, look at the last term. This is a complicated process, right? Each time you don't know how the configuration will look in the next step, because you may either pick up red or white. However, if you are given the information of the previous draws, like whether it was the previous draw, first draw was red or white, then you know the exact configuration of the urn. As here, as in this case, probability of R3 given R1, R2. Here we are told that in the first 2 draws, we have picked up red balls. Given this information, it becomes a lot easier to do, because we know then the exact configuration of the urn, and it becomes trivial to calculate the probability of getting another red ball in this situation. Just one question. Say, if you are asked only this question, what's the probability that the first and third balls are red? That is P of R1 and R3. If you are supposed to find out this thing, then how do you compute such a thing? Then what you can do is you can define another event W2 as the second drawn ball is white. You can identify this event also. Here we are trying to compute probability of R1, R3, that is first ball as well as third ball are red, and nothing is told about the second one. So the second ball is allowed to be of either color. It may be red or may be white. In that case, what you can first observe is R1, R3 is nothing but R1, R2, R3 union R1, W2, R3. Why is it so? R1 and R3 means first and third balls are red. So you are splitting this event into 2 events. First one is the second ball is also red. That means this one. And the other event is first and third balls are red, but the second drawn ball is white. That means this one. There is no other possibility. The second one may be red or white. So we split first this event into these 2 sub-events. Now observe that these 2 sub-events are disjoint because this one tells that the second ball is red, whereas this one says the second ball is white, so they must be disjoint. So probability of R1, probability of, I'm writing here, probability of R1, R3 must be probability of R1, R2, R2, R3 plus probability of R1, W2, R3. It decomposes into these two terms. And once it does so, then it becomes easy to calculate both the terms. We have already calculated this, and by similar logic, you can also compute this term, other term. And once you do both, you know how much should be the probability of R1 and R3. That is probability of R1, R3. And all other events you can take care like this. And the whole scenario, this changing scenario thing, although is very difficult, here is a tool using which you can handle it. That's the end of this session. So hope you understood this session. Here we talked about Bayes' theorem and multiplication rule. Both are very useful and both talk about conditional probabilities. Thank you for listening and see you in the next class.